Hey everyone. So our goal here is to determine whether a mass on a spring, on a vertical spring here, if this force, if this situation is simple harmonic motion, right? So we can be able to determine if a mass on a vertical spring, so this mass here is hanging in the air on a spring, and we want to see if the net force is linear, right? So we want to see if the net force is proportional to x, right, where x is our position. We will be using probably the y variable here, so we're basically going to see if net force is proportional to y. If it is proportional to x, then a mass on a vertical spring is going to be moving in simple harmonic motion. If it's not, it's proportional to maybe the square root of x or x squared or something like that. That is not simple harmonic motion. Right? So we'll suppose here that our spring has some spring constant k, right? And if we hang a mass from this spring, right? So the spring's going to stretch out a bit, and we're going to have this mass here, and if it's just left to its own devices for an extended period of time, it'll settle down its equilibrium position, right? So equilibrium means net force is equal to 0. So if I were to draw a free body diagram here, we've got two forces acting on this spring. We have two forces acting on this mass. We have the weight of this block. So whatever the mass of that block is times the acceleration due to gravity. And we have the spring force acting on this block as well, this mass. And these forces here are the same magnitude. All right, so if I were to write an equilibrium equation here, right, so we sum the forces. So we have our net force, which in this case is equal to 0. Is going to be equal, so I'm going to label upwards as my positive y direction. So we're summing our forces in the y direction here, not that there's any forces in the x, but that's going to be equal to a positive spring force and a negative weight added together. That's going to be equal to 0. So basically you have that our spring force is going to be equal to the weight of the block. Well, spring force, that has an equation, and the spring force has the form of k times x, right? So force of the spring is equal to k times x. At least we're dealing with magnitudes here, so that's what we're worried about here. So the strength of the spring force, that's just going to be k times the amount this has stretched is equal to mg. Right, well, let's call this amount that it stretches. Oh, sorry, I'm using y variables here. Let's say this stretches an amount, we'll call that capital W, capital L. Right, so it stretches some length delta L. So we have K delta L is equal to mg. All right, so in a way here, why did I even bother with equilibrium? Since my net force is 0, that doesn't help us see if it's proportional to position or not. I want to actually come up with a formula relationship for L. So this amount that I've stretched is equal to mg divided by k. Right, so you'll see where this comes into use in just a minute, because we're going to look now to see, well, let's displace this mass a little bit. Let's perhaps lift it up a little bit, so then if we let it drop, it'd be going up and down like this. So we're going to raise it up some amplitude, let's say some value y. So if I were to kind of draw this out, we have our spring. Our spring is compressed here. And let's say that this amount that this has moved is y, since that's our height. All right. So if we're summing our forces in this situation, let's see our net force acting on this spring. Well, if we draw a free body diagram here, excuse me, the weight doesn't change. Okay. But now we do have a change in spring force, right? So since we are not stretched as far, our spring force is smaller. Right? Another way you can think about this is with the spring force is restorative, so it's going to be accelerating towards equilibrium. Right? So this is our system here. Since I push it up, it wants to move back in a sense towards the equilibrium position, so our acceleration is downwards. So that's why my net force here is downwards. Well, let's just compute our net force. We're still going to call upwards our positive y. So then we have a positive spring force and a negative weight. And we want to check to see if this is going to be proportional to, well, this time instead of, we're not x, we're using y. So we're going to see if it's proportional to y. Well, here we have net force. Let's see, let's replace our spring force with something we know. We know spring force is going to be k times the amount we displace, which we're calling y, minus mg. All right, so that's nice. So the only thing we have to look now, you might think automatically, oh, this is proportional to y. But we have to check out k, because k may not be proportional to y, or might affect this proportionality. All right, so let's see how it affects things, because we can plug in, oh wait, I messed up. So, sorry, for my spring force here, the amount of displaced is not y, because that's not from equilibrium. It's amount is displaced from equilibrium is this amount delta L minus this amount y, because that's this distance here. All right, so let's cross this out. That's wrong. So this is going to be equal to k times our delta L minus y minus the weight. I apologize for that. So again, we're reiterating what I just did here. So my spring force is the displacement from equilibrium. Well, the equilibrium of the spring is this location here. So it's going to be at least from the point of view of how I'm solving this problem. So it's going to be this delta L, this whole length here, minus this y value. All right, so let's replace our delta L that we found from before into our equation. So our delta L is mg divided by k, that whole thing minus y, that looks like a g, that's supposed to be a y, minus mg. Right. Well, let's multiply things through here. So this is going to be equal to, if you multiply each of these terms by k, we're left with mg minus ky minus mg. Ooh, this is nice, mg's cancel out. So we're just left with our net force is equal to negative k times y. And so for mass hitting from a spring, its net force is proportional to y, which is linear. Right? This y doesn't have any exponent. Its exponent, well, technically is 1. So this is a linear relationship. So a mass on a vertical spring, even though it might be contorted, well, it is affected by gravity, but this gravitational force does not cause the spring to no longer be in simple harmonic motion. The spring hanging from a vertical spring does exhibit simple harmonic motion because our net force is proportional to displacement.